everyone. So this next lesson is we're going to continue talking about limits, but this is getting into what happens when we take multiple functions and combine them together in some way, shape, or form. What happens to those limits that we've been studying? And the short answer is exactly the same thing happens as whatever you're doing to the functions. And that might not make sense to you, but you'll see it in just a minute here. You'll notice that I have this first page all filled in for you. And I initially made a video where I sat and talked through each line of this. And it got very repetitive, and I don't think you really need to hear that. So if you need to fill in this first page, go ahead and pause the video right now and copy in everything you see written in pink, and then start it up again. And I'm going to kind of just give you the rundown of what's happening here. So like I said, what we're going to be looking at is taking two or more functions and combining them some way, somehow. So we might add them together, we might multiply them, we might raise them to a power, we might, divide them. There's all these different ways to combine functions. And we want to know what happens to the limits when I do that. And the short answer is, whatever you did to the functions, that's what happens to the limits. So for example, if I want to add f and g of x together, and I want to know the limit of that new function as we're approaching c, what this is saying is I can just find the limit of f and the limit of g separately and add the two limits together. And that same thing works for just about everything. If I want to subtract two functions, I can just subtract the two limits. If I want to divide two functions, I can divide the two limits. If I want to raise a function to a power, I can just take the limit and raise it to the power. Okay? So all of these I think will make more sense when you actually see some examples, but they're very, very easy, very, very straightforward. The last one, the composite function, that one does get a little more complicated. And so again, if you would like to pause the video so you can write in what you see here, both in pink and green, you might want to write it first so that then you can just focus on what I'm saying. And this is one that I'm going to explain it, but I think that it'll make more sense once we actually do an example of this. So a composite function is when we take one function and put it inside another function. So we apply one function to another. And so the way we're going to work with those, just like we always work with composites, we start on the inside. So I'm going to start with g of x. And the first thing I'm going to do is find the limit as x approaches whatever of g of x. Okay, so that's what you see me doing in step 1 over here. I'm finding the limit as x approaches c of g of x. And let's just say that number is L. Okay? The next thing I'm going to do is look at that outer function, but what I want to consider is what is the limit of that function, but not as we're approaching c. We want to think about what's happening to it as we're approaching this limit. Because when you do a composite, the output of one function becomes the input of the other. Okay, so this is like a y value for the g of x function, but then we're taking that y value and putting it in for x in the f of x function. Okay, and that is just how composites work. You do have to have a function that is continuous. Again, I think that little line there will make more sense once you actually see an example of this. And I also put sometimes you have to consider what direction the function is coming in from. That is a very, very nitpicky example. I think we'll see one in our notes today. If we don't see it in our notes, we'll definitely see it and talk about it in the homework tonight. But let's jump into some examples here so you can see what all of this is actually talking about. So in this next problem, I've got two functions, f of x and g of x. I'm going to see if I can zoom this out a little bit so I can see all of the questions at once. It'll let me zoom, but it won't let me see all the questions. Oh, I might be able to see pretty close to the bottom there. Okay. So we've got two piecewise functions, f and g here. And you'll notice, like for example, the first one, I'm looking for the limit as x approaches 1 of f of x and g of x. So what I'm going to do is I'm going to find the limit as x approaches 1 of f of x, and then the same limit of g of x. So let's see, at 1. At 1, here's f of x. F of x is nice and continuous, so the answer to that is just 3. And then I'm just going to add that, because this is addition, to the limit of g of x at 1. Okay, let's be a little bit careful with g of x here. at 1, we do have a hole in the graph, but remember, limits are concerned with like where are we heading, not where do we end up. And so my limit is still this value here, which is also 3. And so then the answer to this question is just 6. Okay. Okay, let's go over here to this one. This is still limit as x approaches 1, which actually means I'm going to be able to reuse these numbers here, but this time I'm dividing. So we said the limit as x approaches 1 of g of x, which is right here, was 3. And the limit of f of x as we're approaching 1 is also 3. And so I would say 3 divided by 3, and my answer is 1. Okay, this one is saying let's approach 3, but specifically from the left. Okay, so here's my x is 3. And actually on this graph, this is a little bit hard to read. X equals 3. I'm going to call this like 5.5. I might be wrong about that. But that's the closest approximation I can make, is that at x equals 3. Oh, we might be right at 6, actually. Oh, look at me. I'm going to bust out a straight edge here for you, just because I don't want to say it wrong. Okay. So here we are at 3. Yeah, we might be. Yeah, we might be right at 6. So ignore what I said a second ago. Okay. And it does say the limit from the left, so honestly I only care about moving in this direction. However, because it's continuous, it wouldn't matter which side I came from. So that is just a 6. Now let's do the same thing for g of x. Okay, at g of x for x equals 3, there is a break in the graph, right? So technically this limit does not exist, but since we only care about coming in from the left, I'm only looking at this value, which is here, and that is a 1. So I'm going to say 6 plus 1, and we'll call that 7. This is what's referred to as a constant multiple. It means I'm just taking the f of x function and multiplying everything by 3. If we took this entire function and multiplied by 3, it would just make the whole graph bigger, right? And so I want to look at, as we're approaching 4, so as x approaches 4, and this is in f of x, and again, I've got a hole in the graph, but it actually doesn't matter if there's a hole because both sides are still heading the same way. So I'm going to say this is y equals 2. And then all I'm going to do with that 2 is apply this multiple of 3. So I'm going to say 3 times 2, and so my answer there would be 6. Okay? So hopefully you're seeing what I mean, that really we're just, whatever operation you're doing to the functions, that's the operation you're going to do to the limits as well. Okay, let's do a couple more down here at the bottom, and I'm sorry this is so low on the screen. I just want to be able to see the graphs at the same time. So this is f of x minus g of x, and we're looking as x approaches 3. Okay, so let's be careful here, because we said here as x approaches 3 that we were calling that 6. And it is continuous there, which means both sides are heading in the same direction. They're going to land at that point. So I do have an answer for this one. Okay, I do have an answer that this is 6. Okay, but up here we said for g of x as x approaches 3, this limit does not exist. Okay, and so here's kind of my short answer, but I want to talk about why this is a dangerous shortcut to take. This is like 6 minus something that does not exist. And so I know here that my answer is that this limit does not exist because the left and right limits of g of x are not the same. There's a weird thing that can happen, and I don't know if we're going to see it here, but it could come up. Let's suppose you had something where this limit didn't exist. So like, I don't know, this one at x equals 2 doesn't exist, but let's suppose that was happening here at 3. And you had, you know, 2 different limits from the right and the left here, and you had 2 different limits from the right and the left here. If you took the 2 left limits and added them together, or I'm sorry, in this case subtracted them. If you took the 2 left limits and subtracted them, and then took the 2 right limits and subtracted them, and they both worked out to be exactly the same, then that limit would exist. So we wanted to be careful that we don't get into the habit of like, as soon as we see a DNE, we think that the whole answer is DNE. Okay, in this case, it is true. So let me just show you kind of what I mean. My final answer here is that this does not exist. Okay, But what I really should check is the limit as x approaches 3 from the left of f of x minus g of x. Okay. And so let's do this. And we said, I mean, I'm kind of using my numbers from up here in this one. The limit as x approaches 3 from the left is 6. The limit as x approaches 3 from the left here is 1. So this I would say is 6 minus 1, which is 5. And then I would have to look at that limit as x approaches 3 from the right of f of x minus g of x. And from the right, my limit in f of x is still 6 because that dot was continuous. But in this function, my limit from the right is way down here at -3. And so I get 9. And these two are not the same, and that's why I can say that this limit doesn't exist. Okay? But let's say that this 6 was not the same in both functions because maybe the f of x graph was not continuous. So it had two different, limits from the right and the left. If it happened to work out, and this is a super fluky thing, but if it happened to work out where these two were different and these two were different, but then when you subtracted them, they came out the same, then we would say that's our limit. Okay, so I just wanted to throw that out there in case it ever comes up so you don't say like, oh, you never told me that. Okay, last one, a composite one, and these ones can get a little bit tricky. All right, this one we're going to do in 2 steps. So the first step, we're going to look at the inside function. So we're going to take the limit of g of x as x approaches 1. Okay, so g of x as x approaches 1, we already found that limit and we said it was 3. Okay, so that is 3. That now becomes the input on the f of x function. So the next question is, what is the limit of f of x? But we're no longer approaching 1, we're approaching 3. This goes in down here. And so if I look at f of x when x is approaching 3, glad I took the time to bust out the straight edge on that one because we're using that one a lot, and that answer is 6. So that is my final answer to this question. This limit would be equal to that 6 right there. Okay? Okay, let's try another example. Okay, this one looks like fun. This might actually be the same graph we were just looking at. But we've got 3 functions here, and they're written 3 different ways. Okay? So we've got f of x is a graph, g of x is a piecewise function, and then h of x is given to us in a table. And these tables are hard to tell, like without being able to see the numbers in between, it's hard to tell what's happening with limits. But I do want to point this out, and we haven't learned this, we've talked about this, but we haven't learned it formally. But h of x is a continuous function. That means there's no holes, there's no breaks, there's no gaps, okay? This is one of those really boring functions when it comes to limits, okay? Continuous means boring, okay? And so because it's a boring function, the limit as x approaches anything of h of x is always just going to be equal to the function value at that number, okay? We're going to talk a lot more about this idea later on, but when I'm looking for the limit, for example, as x approaches 0, I'm allowed to just say, oh, it must be 1, because we know that the limit would just be the actual dot on the graph, okay? There's not like a crazy hole or an asymptote or anything like that. Okay. If you want to, now would be a great time to pause the video and see if you can answer these questions, and then you can catch back up with me and see how you did. I'm going to just keep kind of cranking away here. So I'm doing x approaches 4, and I have to look at all 3 functions. Okay, so f of x as x approaches 4, that's right here. So my limit for this first one would be 2. For g of x as x approaches 4, 4, I am not worried about there being like a break in the graph, because the only break in the graph I'm seeing here is at x equals 0, okay? And so if we get one like this one where we have to think about 0, then we're going to have to pay a little more attention. But for x equals 4, that's living in this half of the graph, okay? And so I am just going to use the x squared function. And I'll just jot a note down here so you know where this came from. If I'm doing the limit as x approaches 4 of g of x, I'm just plugging it into x squared because that's the half of the graph that this would live on. So that's 16. And then for the h of x function, I am just looking at the value at 4, and so that answer would be 4. And so this would be 22. Okay, f of g of x. Okay, so this is a composite one. This is one that we're going to do in 2 steps. First step, we're going to take the limit as x approaches 2 of g of x. G of x is that piecewise one, but again, x equals 2 lives on this half of the graph, so I'm using the x squared again. So that would just be 2 squared, which is 4. And then I'm taking the limit of f of x, but I'm doing the limit as we're approaching this 4 number. Okay, and so let's see, as x approaches 4, oh, we did that one up here. As x approaches 4, my limit is 2. Gosh, I just keep reusing the same numbers over and over again, but that is my answer. Okay, so far for answers, we've got 22, we've got 2, and now let's do a division one. Okay, so h of x, limit at 0, and it's 0 from the right, but if it's continuous, it really doesn't matter. So if it's 0, then that's going to be 1. Okay, g of x from the right. Now this is where it matters, okay? Because 0 is the place where this graph kind of splits apart. So I have to make a decision about which half I'm going to use. This is 0 from the right, so I'm using this x is greater than 0 part because that's the right side of 0. That's x squared, which would be 0 squared. And so my limit of g of x is just 0. Okay, that's an issue, right? We can't have a limit that's a number over 0. So this, I would say, does not exist, because this function is undefined at 0. Okay. Okay, limit as we approach -2. Well, I know that I'm going to start by multiplying by this 4 that's sitting right here. Now I'm going to look at f of x at -2. Okay, and f of x at -2, I don't know if that's exactly 1, but for the sake of what we're doing, we're going to call this 1. And then h of x at -2 is 2. And so 4 times 1 times 2 is 8. That's my answer there. And then another composite. And again, I'm going to start on the inside here. So I'm going to start with step 1 is let's find the limit of f of x as x approaches 1. Okay? Limit as we're approaching 1 looks like it's 3 on the y-axis. And then step 2 is to take the limit of h of x as x approaches 3. And limit of h of x as x approaches 3 is just going to be 5. And that's my final answer. So that's the big idea. Oh, I'm sorry. I hope you could see those. That's the big idea here with these questions, is that we're just finding the individual limits and combining them the same way that the functions are being combined. We do have to look out for things like places that stuff doesn't exist. We have to look out for when can I just use the function value versus when do I need to, think about a right side and a left side, that kind of thing. And there is something kind of weird and fluky and tricky that sometimes happens with composites. We didn't see one of those here. Do I have another example? I don't think so. But if we didn't talk about it yet, then we'll make sure to talk about it in class when we go over it on homework, okay? But you've got enough to get you started with this material, and then any of the weird cases that pop up, we'll make sure to talk about. Okay, thanks for watching.